In this session, we will focus on computing the present values as well as the accumulated values of the investments based on the force of interest. Like force of interest is nothing but continuous compounding mechanism, and that force of interest is variable during a period. When I talk about a force of interest is constant during a period, probably we can say we have looked at the accumulated value is nothing but accumulation factor is e power delta t, where t is the time period of investment, or the present value factor, whatever is our amount, S naught into e power delta t is the accumulated value, whereas the present value is st into e power minus delta t. So when the force of interest was given, but that force of interest was constant, the present value came out to be the future value into e power minus delta t, and at the same time the future value or the accumulated value came out to S naught into e power delta t. That was quite simple and straightforward when the force of interest was more or less constant. But if it is variable, what I mean by variable is, if you see that this delta is probably following some specific rule, let's say delta 1 between 0 to t1 some time period, or probably delta 2 some other formula where let's say it is between t1 and t2, like that, probably some delta 3 if it is between t3 and t4, and probably delta 4 probably when it is greater than t4. So like this, what could happen is, instead of the interest rate remaining constant during the period, if I see that the interest rate is variable during a particular period, all I would like to look out for is, when I want to find out the integrated, the accumulation factor. See, for us the accumulation factor is like e power delta. So when I want an accumulation factor, I'll take it as e power delta. When I want a present value factor, I'll take it as e power minus delta. So straightforward, e power delta. So because it is continuous in this entire period, in the e power, what I'll do is, okay, e power 0 to t1, I'll say delta 1s ds. I integrate this between 0 to t1. Then similarly at the power layer itself, I'll put all the one. Okay, between t1 to t2, I'll do it as delta 2s ds. Again in the same power between t2 to 3, I'll say delta 3s ds. And finally, let's say I'll look out for t3 to t, delta 4 SDS, especially if I'm looking at a T which is greater than T4, a T which is greater than T4. If I'm looking at a T which is greater than T4, I'll use this entire formula to obtain the multiplication to obtain the accumulation factor of a cash flow, and I'll use minus delta across to get the present value factor. Now with the same example, let's say I want to know what would be the accumulation factor. Probably if T is lying between this one, T is lying between T1 and T. So again, only those two terms will be used, 0 to T1, delta 1s, and here I'll take T1 to only T. I will not go to T2 because T1 is lying somewhere in that group only. So this itself will be my accumulation value. Similarly, when I put minus, this will become my present value. So you should be comfortable in terms of doing the integrations for these things. Otherwise, conceptually, this is the way we try to arrive at the accumulated value of a cash flow, so these are more applicable for single cash flows. Lump sum cash flow, either finding out the accumulated value after a certain point in time, or based on the accumulated value of future, trying to find out the present value associated with it. So that is how we try to find out, depending on where that T is lying and between what interval. So from 0 till that point T, whatever are the intermediate intervals that are there where the deltas are changing, all those are integrated separately for those entire period and then simplified. That is what is the way we compute the present value as well as accumulated value of one single cash flow. Right, once we practice a few numericals regarding the same, you will get a very good comfort level regarding the usages of this integration. But of course, one thing that is expected is you should be quite comfortable with the usage of the various rules of integration and then get into the calculation processes quite comfortably. But in this case, the other important concept which I would like to drive is, apart from the single cash flows, we are also talking about a continuous stream of cash flows. So these are two important items that I am looking at. When I am talking about a single cash flow, we have already seen to find out the accumulated value, we have said e power integral 0 to t delta s ds. And for the present value, we have taken it as e power minus integral 0 to t delta s ds. But when the cash flow, so sometimes it is said that a cash flow, right? We are not talking about one single cash flow. We are talking about a stream of cash flows between a particular period. Let's say A and B. So there is a stream of cash flow between A and B, and during that period we are seeing a variable interest rate delta t. If that is the case, what is the way we look out for the present value as well as for the future value? Straightforward. So instead of one, so for the delta t, the concept is still the same. So if I am watching for the present value, I will look out for integral of minus a to t, because at t, from t I am trying to get the value of from a till t, I am trying to discount this, probably the ds, delta s ds, and of course, so this entire amount, instead of multiplying it with one single constant, we are talking about a constant stream of cash flows. So whatever, let's say I am talking about this as rho of t, this I will multiply it with this force of interest at dt. The same logic if I am talking about a future value from t till b, again the same delta s ds. This is nothing but, this is the way we are talking about the force of interest, and now there is a cash flow which is between a and b, rho of t, and this is multiplied by dt. So this is how we find out the accumulated value when we have a continuous stream of cash flows. This is how we find out the present value when we have a continuous stream of cash flows. So using these two logics, we should be able to find out the present values and accumulated values of a stream of cash flows, where when the force of interest is given and that force of interest is variable, right? And now we'll take up the examples relating to all these four aspects: a single stream, a single cash flows when the variable interest rate is given, finding out the present value as well as the accumulated value of that. Then also I am looking at a stream of cash flows where which are being paid between A and B period, and I am looking at a variable interest rate operating during that particular period, trying to find out the present value as well as the accumulated value. We'll take up the numericals on all these aspects and then try to understand how we use the integration effectively to compute the accumulated value as well as the present value in these cases. Alright. So let's get started into the numericals on this front. Now let's look at the computation of the present value of a series of payments which are increasing by a certain rate for certain period. So I can use the basic fundamentals itself to try finding out the present value. So we can just see a series of 10 payments is received starting from the 7th year onwards. So we are at 0 up to 7 years, no payment. In the 7th year we are receiving a payment. The first payment is 2064 rupees. Each of the next payments is 7.28% greater than the previous one. So 2064 into 1 plus 7.28%. The next again 2064 into 1 plus 7.28% squared. Similarly, one more year 2064 into 1 plus 7.28% cube. And finally 2064 into 1 plus 7.28% to the power 4. So let's say these are the payments from 7. So this is the 7th year one, and for the next 4 payment means 8, 9, 10 and 11. So these are the amounts that are coming out for the next 4 years. 4 payments. So this is 1 year, this is 2, 3, 4, 5. So there are 10 payments. So there are 5 more payments that are there. Right? There are 5 more payments that are there. Probably in the 12th year, 13th year, 14th year, 15th and then the 16th. So these are 5 more payments because there are 10 payments all that are being made. And after that the increase is 8.88% each time. So whatever is this number, if I call it as x, so this x multiplied by 1.088, x multiplied by 1.088, x multiplied by 1.088 squared, 1.088 cubed. These are my overall cash flows. Now these cash flows I want to find out the present value of them. So we can very well take these things as a part of the spreadsheet, right? So year number 0 I don't have, 1, 2, 3, probably I'll go up to 16. Only from the 7th year onwards there is a 2064, and after that this 2064 is getting incremented by 1.0728, becoming this much. So this goes up to 4 payments, which is up to 11th year, but from the 12th year onward this gets incremented by 1.088, which is 8.8%, and this trend continues till the 16th year. So these are the cash flows that are coming out, and these need to be discounted at the rate of 14.5%. So if I want, so these are the time periods of the cash flows. Now if I want the present values for the same, All I am discounting is this particular cash flow divided by 1.145 because I require to discount it by 14.5% to the power this particular period. That will give me the total present value. These are the present values, and finally total present value is nothing but the summation of all these cash flows, which is coming to 6,177 rupees. So when I'm putting it in a spreadsheet, this is the way I'm going to look at it. But the same logic if I have to take it manually. Look at this. The first payment is 2064 V power 7. Let's try one by one. 2064 V power 7 is the first payment. Then we have 2064 into 1.0728. Just wait. So what we have is 2064 V power 7. Then the second one we have 2064 into 1.0728 V power 8. Similarly, I have 2064 into 1.0728 squared V power 9. Then 2064 into 1.0728 cube V power 10 and up to V power 11 is what we have as the first payment to the power 4 V power 11. So then again on this particular number 2064 into 1.0728 to the power 4 multiplied by that 8.8%. So at least up to here, if I am looking at sum of first 5 terms of a geometric progression, what is the sum of first 5 terms of a geometric progression? A into 1 minus r power n divided by 1 minus r. So the same logic if I apply here, 2064 V power 7 is A, 1 minus R. R in this case is 1.0728 V. 1 minus R power N, R power 5 divided by 1 minus R, 1.0728 V. So what we can very well do is we can first find out 1.0728 V. V is 1 by 1 plus I. So okay, from here I will take my numbers. I is 14.5%. So from this I get my V 1 by 1 plus I. So this is V. So I need 1.0 or first let me compute V power 7. The V power 7 here comes out to be around 30.0.3875. Then I also need 1.0728 V. 1.0728 V comes out to 1.0728 multiplied by V 0.93 and that to the power 5. 1.0728 V to the power 5 is this to the power 5. So this is the number. So based on this I can do the computation. Okay, the first part. The first part of the calculation is 2064 multiplied by V power 7 multiplied by here 1 minus r power n, that is 1.07 v to the power 5. This is 1 minus r power n divided by 1 minus r. R is 1.0728V. So the first part of the calculation gave me 3526, and then the same from the sixth period onwards we had this number multiplied by 1.088 v power 12. So these are the things that come out. So probably what could have happened is the first term would have been 2064 into 1.0728 to the power 4 into 1.088. This is the first term, right? This is A into 1 minus r power n. R again is 1.088V to the power 5 divided by 1 minus 1.088V. This would happen to be the first term, right? These are the 5 terms that are there. So this and even this will be here. This would become V power 12. 2064 into this into 1.088 V power 12. That happens to be the second term. Now in the second term also, if I want 1.088V, it is 1.088 times whatever is the V. This is 1.088V. 1.088V to the power 5. This is to the power 5. Okay. V power 12 is one more thing which I require, which will come like with this V. I raise it to the power 12. This is the V power 12. So I think now we should be able to compute the second term. So the second term in this calculation is 2064 times 1.0728 to the power 4 times 1.088 multiplied by V power 12 into 1 minus 1.088 V power 5 divided by 1 minus 1.088 V. Now this is leading to some 2651. So if I try to add up the total present value through this model, which is nothing but the first part versus plus the second part, giving me again almost the same calculation, 6177. So whether we do it with a spreadsheet or through the manual mechanism using progressions, we should understand the process very clearly and then do it. That makes things quite simpler for us when we are trying to evaluate the cash flows and finding out the present value of the cash flows, and from there getting into the computation of the worth of the investment. All right. Yeah. Now let's look at the accumulated value of a single cash flow if at all the force of interest is given. Force of interest is more like a continuous interest during a period represented by delta t. If at all we are given a force of interest and some initial investment, because we are talking about a single cash flow, the question will more or less will be like, I'm investing some X today and the current force of interest is some delta t. If that's the case, what would be the value, let's say at the end of 10 years? The same x, if I have invested once at the rate of delta t every year, which is a continuous rate of interest for the over the period, and what would be the value at the end of 10 years. If that is the case, that is what we are calling as accumulated value, or in some cases we even call it as future value. So I need to find out the future value of a single cash flow if at all I have an force of interest delta t. How do I look at it? It is nothing but whatever is the present investment x into e to the power of, I integrate it from whatever period 0 to some y years. So if I want the accumulation at the end of 10 years, I'll do it as 0 to 10, or some cases the question could be what is the accumulation period, what is the difference in the accumulation value between 10 years and 5 years. So I'll find out 0 to 10 and 0 to 5 and then do the subtraction between the two. Or I could find out what is the accumulation proportion from 5 to 10. The integration will be done from 5 to 10. All we are doing is delta s ds. This is what is the mechanism. So going to the problem, force of interest, there are two forces of interest given up to 8 years. This is the way the interest is applied, and above 8 years it is said that it is a constant 6%, whereas up to 8 years it is observed that the interest actually follows such kind of a pattern. From that standpoint, let's say if I'm going ahead with an initial deposit of 500 bucks, I want to find out what would be the accumulated value at the end of 10 years. So because we are talking of at the end of 10 years, 0 to 8 years it follows this rate, and 8 to 10 years it follows this rate. So just to start off, the accumulated value or a future value is equal to current investment 500 into e to the power of, I integrated between 0 to 10 delta s ds. Now that I know that 0 to 8, this is the delta s I have to use, I'll split this integral into two parts. 500 e to the power of, I'll take 0 to 8, the delta s I take it as 0.07 minus 0.005 s ds. This is what I take as an integral, and in the numerator, in the power, I'll even add from 8 to 10. I'll take it as 0.06 ds. Now this is very clear to integrate. 0.06 ds, the integral, this entire thing is in the power, don't forget about it. 0.06 ds, integration is nothing but 0.06 s, right? 0.06 s, which means 0.06 into 10 minus 8, whereas this part, so this entire thing is in the e to the power itself. 0.07, the integral is 0.07 s, which will be integrated between 8 and 0, minus 0.005 by 2 s squared. For s, the integration is s squared by 2. This could be integrated between 8 and 0. So probably 0.07 into 8, 0.56 minus this s squared, substituting 8 is 64, 0 is 0. So 64 by 2, 32. 0.005 into 32. How much is it? If I compute 0.005 0.005 into 32, it's almost 0.16. So 0.56 minus 0.16 plus 0.06 into 2, 0.12. This entirely is about e power. So it is coming out to e power 0.52, which will this into 500. So finding out e power 0.52 into 500 gives me 841.01. So I can say that if I deposit 500 right now, where the interest rates follow this kind of a pattern, for first 8 years they follow this pattern, and the next for anything beyond 8 years it follows this kind of a pattern. If I want to find out what would be the worth of my investment of 500 bucks at the end of 10 years, I can use this integral form. So if at all we have force of interest kind of scenario, the future value is computed using e power integral of force of interest ds, right? This is a simple way to compute, and depending on for how many periods, if there are different forces of interest for a different time periods, we have to be careful in applying all of them so that we don't make any mistake in the final simplification process. All right. Now let's try computing the accumulated value of a single investment, right? Accumulated value of a single investment, which is going to be invested at some point in time, and I'm checking out what would be the accumulated value after certain amount of time. If we see here, I want to find out what is the accumulated value of 52,500 rupees, which would be invested after 3 periods, not now. After 3 periods, 52,500 would be invested, and I want to know what would be the amount that it will accumulate to after 7 years. If it had been a straightforward interest rate, a fixed interest rate for the entire period, 52,200, 52,500 into 1 plus I to the power 4, it would have been my accumulated value. In case we are having a fixed interest rate during this 4-year period. But what we are saying is, during this 4-year period, the interest rate is having a force of interest following this particular equation. Between 0 to 5, the interest rate is following this kind of a pattern, 0.04 plus 0.003 t squared, whereas between after 5, from 5 onwards, the interest rate is following this kind of a pattern, 0.01 plus 0.03 t. So which means at different points in time the interest rates are different, which means the accumulated value cannot be directly taken as 1 plus I to the power 4. So in this case I can take my accumulated value. We know that the accumulated interest rate factor, the accumulation factor for the interest rates in case the force of interest is given, is e to the power of t1 to t2 delta s ds. This is what was the integration which we were using to compute the accumulation factor. And once we get the accumulation factor, probably I can multiply the same with 52,500 to get my accumulation value. So in this case, I'll take the integration as e to the power of 3 to 7, the definite integral, delta s ds. So delta s ds This will get modified as between 3 to 5 I'll use this equation, and 5 to 7 I'll use this equation. So between 3 to 5 I'll say 0.04 plus 0.003 s square ds, and in the numerator, in the power, I can talk about 5 to 7, 0.01 plus 0.03 s ds. So this integration, if I start doing e to the power of, okay, 0.04 s, this is integrated between 5 and 3, then 0.003 into s cube by 3. This is again integrated between 5 and 3. Again this 0.01 s integrated between 7 and 5 plus 0.03 s squared by 2 integrated between 7 and 5. So this e to the power of, okay, 5 into 0.04, 0.2 minus 0.12. So the first part is 0.08, then 0.03 by 3, 0.001 into 5 cube, 125 minus 3 cube, 27, 98 into 0.001. This comes out as 0.098. Right, 98 into 0.01 working out to 0.01098, and this also can come out 0.01 as 7 to 5, 0.07 minus 0.05 adding up to 0.02, and even this 0.003 by 2 into s squared, 7 squared, 49 minus 5 squared, 25. So 24 by 2, 12. 12 into 0.03, 0.36. So these are the numbers that are coming out. So overall this is working out as e power 0.38 plus 0.08, 0.46, 0.46 plus 0.98, 0.558. So this is what is the multiplication factor that has come out. So the accumulated value for me is 52,500 into e power 0.558. 52,500 into e power 52,500 into e power 0.558. This is what is your accumulated value. So it is going to come out to 91,726. 91,726.67 at the end of 7 years. If I am going to invest 52,500 at the end of 3 years, it is going to accumulate to 91,726.67 at the end of 7 years. If this is the way the accumulation is, if this is the way the interest rates are going to behave between 3 to 7 periods. And now from there the expectation is on find the constant rate of discount per annum convertible quarterly. So probably first I can find out the value of I. Easier to look at. When I have invested 52,500 for 4 years into 1 plus I to the power 4 is giving me 91,726.67. So from here I can get my I 91,000. So from here I will get my I 91,726.67 divided by 52,400. This gives me 1 plus I to the power 4. This entire thing I take to the power 1 by 4, which gives me 1 plus I. Subtract 1 gives me I. So in this case, the interest rate, annual rate of interest is coming out to 14.97%. The I, which is the annual interest rate, constant annual interest rate, is coming out to 14.97. Now from here I can compute the rate of discount. We know the formula for D, the rate of discount, annual effective rate of discount D is IV, which is I by 1 plus I. So the same logic if I apply here for D, I divided by 1 plus I. This is what is the D. So the constant rate of discount annual is around 13.02%. And one more relationship which we have discussed, 1 minus D should be equal to 1 minus D2 by 2 whole squared should be equal to 1 minus D4 by 4 to the power 4 equal to 1 minus D12 by 12 to the power 12. The same logic which we used to use for the interest rates, 1 plus I is equal to 1 plus I2 by 2 whole squared equal to 1 plus I4 by 4 to the power 4 equal to 1 plus I12 by 12 to the power 12. The same logic. So now that I know the D, 1 minus D, and this time I want quarterly, so I equate these two things. So 1 minus D to the power 1 by 4 is equal to 1 minus D4 by 4. So from here, first I will do a 1 minus D to the power 1 by 4. 1 minus D to the power 1 by 4. If I have to do it, it is nothing but 1 minus D to the power 1 by 4. So this much is coming out. 1 minus D to the power 1 by 4 is 96.57%. That is 1 minus D4 by 4. So D4 by 4 comes out as 1 minus of this one. So this works out to be the D4 by 4. From here I get my D4 value, which is the rate of discount convertible quarterly. So this multiplied by 4 is the rate of discount that is convertible quarterly, working out to 13.71%. So I should be comfortable in terms of first computing one of it and from there trying to convert from one form to the other to achieve that comfort level in the working part. Alright. So that is how we try to find out the accumulated value given the force of interest across multiple periods, and based on that we can try to find out the constant rate of interest for that entire period, which can again lead to finding out the nominal rate of interest or discount compounded at various convertible at various frequencies. All those calculations can be done by using this kind of equality relationship. Alright. Now let's try to look at finding the present value of a discrete cash flow. Until here it looks quite comfortable. Present value of a discrete cash flow, but given a force of interest, not a discrete interest, not at the end of the period or at the beginning of the period. We are given delta. So if at all I have the delta, how do I get into the computation of the present value of a cash flow? So here we are saying that force of interest is a function of time. So which follows this particular form between 0 to 5 years, and if my investment is for more than 5 years, the delta t is constant. So if I have to convert this delta t V form, derive and simplify as far as possible the expression for V of t. So we know that if I want to find out V of t, which V of t is nothing but a discounting factor of a cash flow of 1 received at the end of t period, right? V of t is nothing but at the end of t periods, if $1 is going to be received, what is the present value of the same? So when I am looking at that V of t, I can very well write it as e power minus integral of 0 to t. Here I have to see, depending on whether we are talking about t greater than 5 or less than 5, we'll come to it. E power minus 0 to t delta s ds is the regular usage for finding out the V of t. Right? Now, depending on whether t is less than 5 or greater than or equal to 5, we will have to change the appropriate mechanism. So, if it is less than 5, I could directly use this mechanism itself, e power minus 0 to t delta s between 0 to 5 years is this one. So I'll write it as 0.04 plus 0.02 s ds, right? So this gets written as 0.04, the integral of 0.04 is 0.04 s, and between, okay, I'll write it minus e power minus 0.04 s, and for this 0.02 I have s squared by 2. These are the numbers which have to be integrated between t and 0. So overall I can very well write it as e power minus 0.04 t plus 0.02 by 2.01 t squared, and 0 substituting is always a 0 itself. So especially when I am looking at between 0 to t, the V of t, I can directly take the V of t as e power minus 0.04 t plus 0.01 t squared. Then how about if I am looking at between t is greater than 5? Again the same logic, e power minus 0 to t. Here the point is, okay, if it is greater than 5, up to 5 I can directly use this particular, so initially I'll write e power minus 0 to t delta s ds, but of course delta s is different at different intervals of time. So I will write it as e power minus 0 to 5, because I know that t is definitely greater than 5. 0 to 5 I will directly integrate 0.04 plus 0.02 s ds, and at this integral level itself I will add up phi to t. I'll take phi to t 0.05 ds. So obviously it is coming out to e to the power of minus, okay, 0.04 s plus 0.02 s squared by 2. This has to be integrated between 5 and 0, and in the exponent itself I have 0.05 s, which has to be integrated between t and 5. So this part is direct, e power minus 0.04 into 5, 0.2 plus 0.01 into 5 squared. 0.01 into 25, which is 0.25, right? 0.25. And at this, again, this is becoming 0.05t minus 0.05 into 5, 0.25 again. So this is what is coming out. So the integral is becoming e power minus of, these two are going off, 0.05t plus zero point 0.2. So this is what is the expression if you are seeing that t is greater than 5. If you see that t is less than 5, we can very well go with the other expression which we got, which is e power minus of 0.04t plus 0.01t squared. So this is when t is less than 5. This is the expression for v of t. When t is greater than or equal to 5, this is the expression for v of t. Now either I can use these expressions directly and find out the next one, like present value of $2,000 or 2,000 pounds that is due at the end of 12 years. If I want to find out the present value of that, I can directly substitute it now. E power minus 0.05 into 12 plus zero point 0.2. That's it. So which will take it to e power 12 into 0.05, which is around 0.6 plus zero point 0.2, making it e power minus 0.8. That I am multiplying by 2000. So overall it may work out to 2000 into e power minus 0.8. So just simplifying the same, 2000 into e power minus 0.8. So the present value of it is working out to somewhere around 898.66. So the present value of this, whatever I am going to get after 12 years, the 2000 which I am going to get after 12 years, the present value of that as per this interest rate mechanism is going to be 898.66. Here we have to understand that VT is something that has helped me to find out the present value of a lump sum payment that I am going to get in future at time t, and this is nothing but e power minus delta s ds. But if it had been the future value or accumulated value, I could have taken it as e power delta s ds, no minus sign, that's it, rest all remains the same. So it has to be a careful evaluation of the integral. We'll take a couple of more practical ish problems also to try to address that, but at least trying to solve the integration equation should be more comfortable. Now calculate the rate of interest per annum convertible monthly. Based on this above transaction, I want to find out what is the rate of interest per annum. Now I have invested 898.66, right? 898.66 at some particular rate, 800. So it is as good as saying 898.66 if I invest at the rate of I. Of course, because I need convertible monthly, I can take it as I12 by 12 to the power of 12 years. So 12 into 12, 144. I12 by 12 to the power of 144. This is fetching me 2000. Right? Because I am looking at the interest rate per annum convertible monthly. right? Otherwise, it could have been first find out the annual interest rate I, and based on that you convert it into I-12 monthly. Okay, it's other way of talking about is 898.66. I have invested for 12 years. It has resulted in 2000. That is giving me the effective annual rate of interest. So based on this, I will get 1 plus I to the power 12 is equal to 2000 divided by 898.66. So if I do that, 2000 divided by 898.66, this is 1 plus I to the power 12. So from here I can get my 1 plus I. So this to the power 1 by 12 will give me 1 plus I. And from here the I is coming out as this minus 1. So 6.89% is the effective annual rate of interest in this case. But now what we want is this is same as 1 plus I-12 by 12, right? This I 1 plus I-12 by 12 to the power 12. This should be the same as 1 plus I. So from here I can find out this should be same as 1 plus I. So based on this simplification, I can get 1 plus I-12 by 12 is 1 plus I to the power 1 by 12, and I-12 by 12 is equal to 1 minus of 1 plus I to the power 1 by 12. So right, 1 plus I by 12 to the power 12 is 1 by, so all we are saying is 1 plus I-12 by 12 is 1 plus I to the power 1 by 12. So from here I can very well find out my I-12. Right here I can very well find out my I-12. So probably what I can do is 1 plus I, this is 1 plus I to the power, do it as 1 by 12. So this to the power 1 by 12 is giving me 1.005. This is 1 plus I to the power 1 by 12. So if I just want I-12 by 12, it is 1 plus I to the power 1 by 12 minus 1. So this minus 1 is giving me I-12 by 12, and this I multiply it by 12 gives me I-12. So I-12 is giving as 6.68%. This is the nominal rate of interest convertible monthly. If I want to know the effective annual rate of interest, I can take it as 6.89%. But if I want the nominal rate of interest per annum convertible on a monthly basis, it is equivalent to 6.68%. So this is one way I can try finding out the present value of the cash flows when a force of interest is given, and from there probably I can even try to convert that present value or that interest rate into a monthly convertible interest rate or effective annual interest rate, any such kind of calculation. So these formulas need to be comfortable with for doing this kind of conversion transactions or equivalent comparison things quite effectively. Alright. Now let's look at one more important numerical relating to finding out the present value of a stream of cash flows, especially when two different sets of cash flows are occurring at two different points in time. Probably there is at one point in time between the period of 2 to 4 years, there is a continuous stream of cash flows, and probably at time 6 there is one single discrete cash flow occurring. But in this whole process, we are seeing that the force of interest is variable during this period. So it's a slight complication of both the streams of cash flows as well as the variable interest rates, which is resulting in trying to find out the present value of the entire thing and helping the investor compute what should be the price that needs to be paid for this investment. So what we are looking at is we'll try to solve both of them one by one. So first let's look at the first part, right? So between 2 to 4, this is the continuous stream of payment that is coming up. So between 2 to 4, the interest rate is going to be this one. So probably I could have, first I can calculate the present value factor associated with this. What is the present value factor associated with this? E power minus integral of 0 to t, right? If I want the present value factor associated with this, I am taking it as e power minus 0 to t 0.07 plus 0.002 s ds. So we can find out the present value factor for this, saying okay, e power minus this part is 0.07 s being integrated between t and 0. Similarly, 0.002 s squared by 2 being integrated between t and 0. So the numerator, so this present value factor is becoming minus of 0.07t plus 0.001 t square. This is what is becoming the present value factor. Now all I can do is, this is the cash flow that is coming to me between period 2 to 4. So between 2 to 4, I'll take this cash flow constant, I'll take it outside, 500 e power 0.1 t plus 0.001 t squared. This is the amount, and the present value factor here is coming out e power minus 0.07 t minus 0.001 t squared. So probably I can take these things out. So it is really working out as 500 into 2 to integration between 2 and 4 e power 0.1 t minus 0.07 t dt. So probably this is becoming 500 into the integral between 2 to 4 0.03 t dt. So which is helping me to solve this integral. E power ax is e power ax by a. So this is becoming e power 0.03 t divided by 0.03, and this is integrated between 4 and 2. So it is working out to 500 by 0.03 multiplied by e power 0.12 minus e power 0.06. These are the numbers, right? 500 by 0.03 into e power 0.12 minus e power 0.06. So just taking those calculations, 500 by 0.03. Okay, I'll take 500 by 0.03, giving me this much. E power 0.12 minus e power 0.06. E power 0.12 minus e power 0.06, helping me to find out that value. So overall it is coming out to this number multiplied by this number. So which is working out to 1094.338. So the present value of this, the present value of all this first part is 1094.34. Now I can look out for the second part. A payment of 15,000 is coming at time 6. So for time 6, first let me calculate the present value factor. See, any present value factor is e power minus 0 to t delta s ds, straightforward. So here because we are talking about 6 period, so the delta s will include both of them. So it becomes e power minus 0 to 5, this one 0.07 plus 0.002 s ds, and here we have it between, this entire thing should be in minus 5 to 6, because here I know that the period is exactly 6, not anywhere between 6 or something. So 5 to 6, I'll take it as 0.085 minus 0.001 s ds. Right, this is what is going to come up. This is what is going to come up for this present value factor. So this is, let's simplify this part, the integration part. 0.07 into 5, 0.35 plus 0.001 into 25, 0.001 into 25, making it 0.025 plus 0.085 into 1, 0.085 minus 0.001 by 2, 0.0005 s squared, right? 0.0001 by 2 into s squared, 36 minus 25, 11. So probably it is becoming 0.011 divided by 2. So 0.00505. Right, so this is becoming 0.00505 is what is becoming this particular factor, right? And probably if I want to know the present, so probably let's simplify this part. 0.35 plus 0.025 plus 0.085 minus 0.00505, 0.00505. So this is this much. So I'll take e power minus this much, so giving me 0.63, and I'll take 15,000 multiplied by this much, giving me the present value of that 15,000 to the current time period. So this is the cash flow present value corresponding to this 15,000, whereas this is the cash flow that is corresponding to this payment stream received between 2 to 4. So the overall the present value of my cash flows is the summation of this along with this. So overall 10,611 10,611 should be the price which the investor needs to pay for the instrument which is having this kind of characteristics. So in simple, it's like if at all I want to solve these kind of numericals, the way I should look out for is first find out the present value factor, wherein it's as simple as finding out e power minus integral of 0 to t delta s ds. Depending on whether this t is spanning over 2 periods or 1 period or 3 periods, we'll use the appropriate deltas and try computing this e power minus that present value factor. After that, you directly multiply it with the cash flows. If it is a continuous stream of cash flows, put the integration factor for that continuous stream of cash flows. Otherwise, take it as discrete and then try solving the expression directly. So that is how we should manage of the various cash flows, the present value computations for these various cash flows, which can help us in in working out the compounded kind of interest, or the variable force of interest rates, as well as the various variable payment cash flows that are occurring at various points in time. All right. Now let's look out for not a discrete cash flow but a continuous stream of cash flows given again a force of interest. So during a particular period, I have a continuous stream of cash flows. It's not at the end of this year, between 6 to 10 years in this numerical, between 6 to 10 years. So it's not something at the end of 7th year some cash flow, at the end of 8th year some cash flow. During this entire period, at the rate of 10 into e power 0.01t. So in this entire period we got 10 into e power 0.01t, but on a continuous basis. Again here we got 10 into 0.01t on a continuous basis, on a continuous basis, on a continuous basis. If that is the case, and this is how the interest rates are behaving between 6 and 10, how do I typically find out the present value? If it is only the force of interest, see, between 6 and 10 means the whole period falls only into this force of interest. So first of all, when I look at the force of interest, which is nothing but e power minus 0 to t delta s ds, which I have to apply this part. So it comes out as e power minus 0 to 5 0 to 5.04 plus 0.02 s ds plus 5 to t 0.05 ds. This is what comes out, and on the simplification, as we have done in the earlier numerical, this entire thing will come out as 0.2, and this is 0.02 into s squared, 25 squared, which comes out to 0.25, and this will come out as 0.05t, and this will come out as minus 0.25. So the overall thing is coming out as minus of 0.2 plus 0.05t, at least up to here, which is the force of interest. So which is talking about $1 payment. Whereas now when I am looking at a continuous stream of payment between 6 and 10 years, right, the continuous stream of payment between 6 and 10, now I will integrate between 6 and 10 again, because there is a continuous stream of payment of 10 e power 0.01t. This is the amount, and I have to multiply it with the present value, which is e power minus 0.2 plus 0.05t. And here I have, so this entire thing needs to be integrated between e power minus, so this is the relationship, 10 into e power 0.01t. I am integrating it to the in the amount that minus 0.2 plus 0.05t. This entire thing is integrated on the t. So simplifying this, it is coming out as integral between 6 and 10. The 10 I can take out constant, e power minus 0.2 also I can take out constant. So this is becoming e power 0.01 minus 0.05. minus 0.04 t dt. So this is becoming 10 into e power minus 2.2 into the integral of this e power minus 0.04 by minus 0.04, this being integrated among 10 between 10 and 6. So the left hand side, I mean the common side without the integral, if I compute it, 10 into e power minus 0.2 divided by minus 0.04. 10 into e power minus 0.2 divided by minus 0.04. This is working out to minus 204. Okay, minus 204 into e power minus 0.04 into 10. 0.4 minus e power minus 0.24. So again this I am multiplying this with minus 204. So I have to compute e power minus 0.4 minus e power minus 0.24. So this is what I have to multiply it with. So these two numbers multiplied is what giving me as 23.80. So 23.80 forms the present value of this kind of a payment that I am receiving each of the years on a continuous basis over the entire period, using again a force of interest also. So first thing I should look out for is simplify it for the force of interest during that period and then apply that force of interest, because once I am simplifying the force of interest, all I am getting is Vt. So whatever is the cash flow, I integrate that cash flow over the Vt. I integrate that cash flow over the Vt, because if it is a single stream of cash flow, it is just Vt. But if it is multiple streams of cash flows, again those all cash flows need to be discounted to the present value. And if that cash flow is a continuous stream, it requires another integration, because we cannot simply sum up the various cash flows to find the present value. We are doing an integration over that entire period of the cash flows per annum, multiplying it with the Vt per annum kind of a scenario. So that is how we try to compute the force of the compute the present value given a force of interest per a continuous cash flow. All right. Now let's look at computing the present value of a continuous stream of cash flows. Right, we'll look at computing the present value of not a single cash flow but a continuous cash flow given a force of interest. Force of interest is always represented by delta t, which is a kind of a variable. The interest is not a fixed interest, but it varies as per a particular pattern during a time period. So here it varies at the rate of 0.07 minus 0.005 t between t equal to 0 to 8, and it is 6% constant when t is greater than 8. So whenever the force of interest is given and we have a future payment, let's say the future payment is some x, then the present value is e to the power of minus integral 0 to t delta s ds. This is what is the typical mechanism which we use to find out the present value if x is a kind of a constant payment. So in this case, let's assume that x 200 into e power 0.1 t is a constant payment, if at all. If at all it's a constant payment, but the question is it's a continuous payment. So if at all it's a one-time payment, then the present value would have been 200 into e to the power of 0.1 t into, that is equivalent to x, into e to the power of minus 0 to t delta s ds. And now that it is a continuous stream of payment between 10 to 18, this entire thing I integrate it between 10 and 18. And whatever I get, this is what is the present value of this continuous stream of payment. And regarding this, I'll use two different values. Between 0 to 8, I'll use this expression, and greater than 8, I'll use this expression. So just to simplify the scenario, right now I'll take a fresh sheet of paper to work out on this. So if I go for a blank screen, or probably I'll take a white screen, wherein alright, let me write it here itself. So integral 10 to 18, I'll write it step by step. 200 e power zero point 1 t into e to the power of minus integral, I'll take it as 0 to 8.07 minus 0.005 s ds, and this power again would be from 8 to t. I don't know, because it should be between 10 and 18. T can be anywhere between 10 and 18, so I say 8 to t 0.06 ds. So what will happen, the power, so the first part of it I'll keep it aside, 10 to 18, 200 e to the power of 0.1 t. This, okay, if I start working out on the integral, 0.07, the integral is 0.07 s. So s means I'll take it as 8 minus 0 minus 0.005 s is s squared by 2. So by 2 into s squared, 8 squared minus 0 squared. So this becomes 64 plus 0.06, if I am integrating 0.06 s. I'll take it as t minus 8. So this is the evaluation of the inside integral. So this will still remain 10 to 18, 200 e to the power of 0.1 t, whereas this one becomes e power 0.07 into 8.56 minus 0.005 into 32.16, and this becomes 0.06 t minus 0.48. This entire thing is integrated with dt. So this becomes 10 to 18. It's a step-by-step evaluation process. 200 e to the power. Okay, I have a 0.1 t here and 0.06 t here. So taking it to be, and this entire thing is actually with a minus. So probably this becomes minus, this becomes a plus, this becomes a minus, and this becomes a plus. So 0.1 minus 0.06, it becomes 0.04 t. And what about the constant part? Minus 0.56 plus 0.16 plus 0.48 plus 0.64 minus 0.16. So this becomes 0.08 dt. So this again gets simplified when I am integrating it between 10 and 18. I can take the constant outside, 200 e power 0.08. This entire thing is a constant. So I can just integrate e power 0.04 t dt. So this becomes, now I'll take the integral. So the constant, I'll take it outside. Integral of 0.04 t e power 0.04 t is nothing but 0.04 t by 0.04, and this is integrated between 18 and 10. So just to simplify it, 200 by 0.04 is 5000, 5000 e power 0.08. Now the simplification part comes. Okay, I'll take 200 into e power 0.08, this divided by 0.04, this value divided by 0.04 is 5416, and this is e power 0.04 into 18 is 0.72 minus 0.4, right? E power 0.72 minus e power 0.4. What is the value of that? E power 0.72 minus e power 0.4. This much. So I multiply this number with this number, saying 3047. So the present value of that entire continuous stream of payments that I am getting during the 10th to 18th years, in between 10 to 18 years, at the rate of 200 e per 0.1 t, the present value of that entire stream of payments, I can simplify it as 3047.33. Right? So just to simplify it, whenever we have two things, force of interest, when I am finding out the present value using the force of interest, this becomes e power, the integral will come, which is the force of interest minus the force of interest. If at all the payment stream is also continuous, then whatever is the payment stream, that gets integrated over the period of payment. This entire integration simplified is what will give you the required result. Alright. Now let's look at computing the accumulated value of an investment, where there are one continuous stream of cash flows, different amounts at different points in time, and also the force of interest is also different at different points in time. We are not talking about a constant force of interest. The force of interest also is different at different points in time. So we have delta t being given as 0.2 minus 0.01 t, and at the same time we had amount wise, you see, initially paid at the rate of 200 per annum, but decreases linearly to 100 per annum after 10 years. So obviously, because it's on a linear decrease, I could very well write the amount. The amount I could have written it as 200 minus 10t. Because when t is 0, it is 200, and when t is 10, it will touch 100. So there is a linear decrease for the same. Now, using this too, if I want to find out the accumulated value at the end of 10 years, all I am doing is an integration between 0 to t, the amount, a continuous stream of cash flows, which is this amount, e power delta t dt or delta s ds. So basically between 0 to t, I am looking at delta s 0.2 minus 0.01 s ds. So we'll try to first integrate the exponent part, and then we'll try to take with the cash flow. So only this part, when I'm trying to do the integration, it is nothing but e power 0.2 s minus 0.01 s squared by 2, this being integrated between t and 0. So it becomes 0.2 t minus 0.005 t squared. So this is the interest rate, and this the cash flows are also changing. So we'll find out the accumulated value using 200 minus 10t into this. So I have to integrate this entire thing in the dt range. So from there over the 0 to 10 years period. So for that I could very well assume, let's say I take 0.2 t minus 0.005 t square as some p. Then what is happening? I take the differentiation 0.2 minus 0.01 t dt equal to dp. So here I am able to write zero point 0.2 into 0.2 minus 0.01 t dt equal to dp. So in terms of dt, I could write it as dp divided by zero point 0.2 minus 0.01 t. I take it back here, integral, okay, now 0 to 10, right? So the integral also changes now. If I substitute 0, obviously p is 0, so the downside limit is still 0, whereas what about the upside limit? When I substitute t equal to 10, 0.2 into 10, 2 minus 0.005 into 10 squared, 100, 0.0, so which is minus 0.5. So this is p is fluctuating at around 1.5. So the limits are changing, 0 minus 1.5, then 200 minus 10t. What would happen to 200 minus 10t? Okay, I'll take 200 minus 10t into this. I can take it as e power p, and in case of dt I will take it as dp by zero point 0.2 minus 0.01 t. If you see this is nothing but 100. Sorry, 0.01 t is also within the bracket. So if you see this is nothing but 100 into point. See, if I do 1000, sorry, 1000 into 0.2 t, it 0.2, it becomes 200, and 1000 into 0.01, if I do it, it becomes 10. So this divided by this is exactly 1000. So all I could have done is 0 to 1.5, 1000 e power p dp. So which is again giving me 1000 into e power p. I integrate it between 1.5 and 0, which makes it 1000 into e power 1.5 minus e power 0, which is 1. So if I do this, that is what I will get as the present accumulated value. So all I could have done is e power 1.5 minus 1. This is coming out to 3.4, and I do the 1000 on that. Let me check out. 0.2 into 10 is 2.005 into 100. So P is becoming 1.5, 1000 into e power p dp. So e power p is the integral, and I am integrating it between. All right. So which is giving me 3.48, and multiply it by 1000. That number I am multiplying it by 1000 to get 3481. That would become the accumulated value, but it's not looking like that because 200 per annum. Let me just check out what has gone wrong somewhere. Okay, for the force of interest, I have to take it as e power minus. In this whole stuff, this entire thing is working out to minus. So obviously, I'll have my final answer as e power minus 1.5 minus 1. So instead of taking e power 1.5, I should have taken it as e power minus 1.5 minus 1, which is creating so because there is a minus, it would be a sign change. So a sign change is giving me 776.86. 776.86 is the accumulated value of this annuity. See, when we are talking about getting the discounting factor, right, we are talking about a force of interest. We are trying to find out the present value of that force of interest over the entire period. Calculate the present value of the continuous annuity payable. We are not talking about the future value. If it had been the future value, then here we have the first question as calculate the present value of a continuously payable annuity. But if I am talking about the future value, accumulated value after 10 years, then I could have directly taken it as e power delta itself, which could have worked out to 3481, which we have got in the earlier case. So the present value is 776 and the future value is going to be 3481. So we have both the accumulated value calculation as well as the present value calculation using this stream of continuous stream of cash flows. Alright. Now let's look at finding out the accumulated value of an investment in terms of continuous cash flows and force of interest. Both of them being given. Continuous cash flows, one particular rate at which the cash flows are moving every year, and at the same time the interest rate is also on a force of interest or on a continuous basis. When these two are given, okay, we know that first of all the accumulation factor is nothing but e power integral of 0 to t delta t dt. When the force of interest is given, the accumulated value is e power 0 to t delta t. But if the cash flow itself is an accumulated cash flow, then probably is a cumulative or is a continuous kind of a cash flow. This is over a 10-year period, so this goes as e power 0 to t1, then whatever is the row of t into e power this dt. This is what will go as a part of the continuous stream of cash flows as well as the force of interest if I have to find out the present value or the accumulated value of the investment. So what we can do is first let's simplify this in terms of t and then we'll do this part. So the accumulation factor for me comes out as e power 0 to t delta s ds. Delta s is given by 0.05 plus 0.01 s ds. Solving for this, we get e power 0.05 s plus 0.005 s squared. Or probably here we are integrating it between 0 to t. So we get it as 0.05t plus 0.005t squared. Now the same logic, if I extend it, right, the same logic if I take for cash flows, integral 0 to t, or here in this case we are talking about a 10-year period. So integral 0 to 10 plus 2t into e power 0.05t plus 0.005 t squared dt. This is what is our required expression. So from here you can write it as, we can take out, probably we will write this as integral 0 to 10 plus 2t. This will take out e power 0.005 out. Then it becomes 10t plus t square. This is what will be the numerator. Once I take out 0.005, so this we can take out the constant out, e power 0.005 into e power into 0 to 10 integral 10 plus 2t into e power 10t plus t square dt. Now this particular power 10t plus t squared is what I will take it as some p. So 10 plus 2t dt comes out as dp. So instead of 10 plus 2t and dt, I will write it as dp. So this becomes 0.005 integral. We'll try to write the limits. So it becomes e power p dp. So what are the limits here? I substitute t equal to 0, p is also 0. I substitute t equal to 10. P becomes 10 into 10, 100 plus 100, 200. So 0 to 200 e power p dp. So this actually becomes e power p itself. Right? This becomes e power p only. So 200 to 0. So all we can write it is e power 0.005 into e power 200 minus e power 0. The other way we could write it is e power 0.005 into e power 200 is e power 1 minus e power 0.005 multiplied by e power 200 minus 1. So we can multiply we can very well multiply these e power 200 minus e power 0, e power 200 minus e power 0, which is this much. This you multiply with e power 0.005. Sorry, there is something gone wrong. E power 0.00. Okay, this is e power 0.005 to the power. Right? I have to raise. It's not. See, this is not a constant out. This probably is going e power 0.005 into this. So it's not a plus. So the way I will take this out is this e power 0.005. I have to, this is the multiplier, right? Okay, let me come back again. E power 0.005 if I am taking out, this is becoming 10t plus t squared. Okay, let me not take out anything outside here. So 10t plus t squared, if I am taking it as p, this is becoming e power 0.005p. Probably let me rewrite it there. So this is becoming e power 0.005p dp. So the integral is becoming e power 0.005p divided by 0.005. This is being integrated between 200 and 0. So this is working out to 1 by 0.005 is 200. This 200 I am multiplying it with e power 0.005 into 200, e power 1 minus e power 0. 200 into e power 1 minus e power 0. That is what is the calculation. So I will take the accumulated value as 200 multiplied by e power 1 minus e power 0. Let's see. So it is coming out to 343. So whatever is being paid over this 10-year period at the rate of 10 plus qt, over a 10-year period it is getting accumulated to 343. Right, that is what is getting accumulated over this 3-year period, because normally e power 1 minus e power 0 is around 1.71. I am multiplying the 200 with that 1.71, giving me 343 for this period. So the accumulated value of this stream of payment that is coming up at different points in time over a 10-year period is working out to this much of amount. Alright.